All right, welcome to the Link Labs webinar, LPWA in an LTEM and narrowband IoT world. How's that for an acronym-filled mouthful on such a day as today? All right, going to jump in here. I'm Brian Ray. I'm the founder and CTO of Link Labs here in cloudy and rainy Annapolis, Maryland. And thanks to everybody who joined. We had 2,300 people register for the webinar, which is really amazing and shows that there's a tremendous amount of interest worldwide in this technology. So I'm going to jump in. Our agenda today is we're going to cover what is LPWA, what is the history of LPWANs. We're going to go into some technology snapshots of different providers, different technologies in the space, and then go through some flows and some basically workflows on how to pick different technologies. And then we're going to jump into some use case examples, and then take as much time as we need to answer your questions. I'm actually joined here today with Reed Fawell, who's our Chief Revenue Officer, and Glenn Schatz, who's our VP of Business Development. So if you hear somebody chime in off camera reminding me to address something that I forgot, that's who that is. For questions, instead of using the questions tool here in the Zoom meeting, we are going to take questions on our forum site. This will allow us to go back through and answer any questions that we don't get to. A lot of the questions that have been coming up already are pretty technically detailed, and I think it's important that we answer those. Given the size of the audience and the varying levels of technical sophistication, I don't want to get too far in the weeds, or we're going to have people falling asleep here after lunch. All right, so what is LPWA? LPWA, if you don't know, then I applaud you for being on this webinar despite that, but it stands for Low Power Wide Area Networks, which is a phenomenon that has really come to the forefront of the market in the last few years, and it's been driven by advances in chip scale technology that through a combination of increased sensitivity, coding gains in the chip, and very low data rates, down to hundreds of bits per second, or like 300 baud, aka dial-up modems back in the 80s, you get really long range. Another feature of the systems is multiple access, or one-to-many architecture, where you have a single gateway that's talking out to hundreds or thousands of end nodes in the network. When people say LPWA, they also generally are talking about unlicensed spectrum, which is using the sub-gigahertz UHF technology that is available in 868 megahertz in the ETSI rules, or in Europe, and the 900 megahertz UHF under the FCC rules. And then there's a big distinction between carrier deployed networks, which are your Sigfoxes, Ingenues, AT&T, Verizon, versus customer deployed or application specific networks that get deployed in a really deploy it yourself model. A little bit of history of LPWA. If you're not aware, this space has really been building for a lot longer than some people think. Going back to the 90s, technologies like AlarmNet and Artis, were using licensed spectrum to, create these types of networks. And then you had GPRS, which is General Packet Radio Service, which became 2G in the 2000s. That was really the forefront of M2M type communications, where you had, fleet telematics and other devices that were transmitting IP or datagrams back to the carriers. This company, OnRamp, has actually been around for a long time. They're the company that eventually became Ingenu, which is deploying wide area networks using a 2.4 spread spectrum technology. And then really the company that is responsible for really establishing the space and creating the market, which is Sigfox, was established in the late, I think around 2009, if I'm not mistaken. And Sicleo was a small company whose technology was acquired by Symtech, and that is what became the basis for the LoRa technology that the LoRa Alliance and others have adopted. Fast forward 2014, there's been a whole bunch of companies, including Link Labs, that have sprung up in the space. You have the LoRa Alliance companies, of which there's hundreds. And then, the 3GPP, which if you're not familiar with 3GPP, that's the standards group or body of standards bodies that standardize the cellular technologies. And they've been quick to address the untapped needs that this market has apparently created. And so definitely throw them in here as a late addition. And I'm going to actually jump into the 3GPP technologies first, because I think that is some of the things that people are most interested in on today's webinar. One, just a quick word about licensed versus unlicensed spectrum. You know, if you're a wireless engineer like me, this is secondhand, but for those of you that are new to the space, it's a really important distinction that there are bands of spectrum that's allocated by the government for shared use, everything from cordless phones to baby monitors to Wi-Fi to Bluetooth. These devices, while they have to be certified for operation, they're not licensed. The spectrum that your cell phone uses is licensed by the government because those very sophisticated wireless technologies can't exist well in spectrum where you have unmanaged interference. So in the 900 megahertz band, you can see this spectrogram down here at the bottom, which is in New York City. You can see that even from the ground in New York City, you're getting 20 to 30 dB of noise floor elevation, and just kind of broadband noise, all sorts of messages from everything from smart meters, baby monitors, etc. And so trying to operate a wide area service especially in the 900 megahertz band in cities is really challenging, because not only do you have the Part 15 or the low power devices, of which LPWAN would be one, you also have licensed users where the FCC has granted licenses to operate at high power inside of that same band. Additionally, just outside the band on the upper end, you have the high power downlinks of mostly paging operators that are transmitting up to 1 kilowatt just outside the band. So if you're up on top of a building or up on top of a telecom pole, you could be taking a lot of energy just outside of the band, and that's going to bleed across your front end and cause, decrease in sensitivity. And so the takeaway here is that if you're using unlicensed spectrum, you can't count on band quality, and that's why at Link Labs we often deploy this unlicensed technology inside of a building or for application-specific reasons where you're not up high taking in all the noise that might be available on the air in the city. All right, I'm just going to jump right into the 3GPP technologies that have come to the forefront of the LPWAN space. The first is LTE Cat M1, and what LTE Cat 1 is LTE, like 4G LTE, which is just like you're familiar with your handset. They've taken the 20 megahertz spectrum from LTE, and they've said we can operate a lower data rate connection with inside one resource block in one time interval, which gives you a much simpler front end that only has to digitize 1.4 megahertz of spectrum versus a whole 20 megahertz spectrum, and allows the device to have only one antenna. And what that means is you can have a much simpler and less expensive chipset. It's half duplex, meaning it only has half the processing power because it's never transmitting and receiving at the same time. And then 3GPP actually, as part of release 12 and 13, standardized 2 power saving features that have been really critical to driving the types of long battery lives that could be achievable on Cat M1. The first is power saving mode, and this is where the device can tell the base station or tell the network that it's going completely dormant and going right down to idle for an undetermined amount of time, as long as it wakes up once a day to check in and tell the network that it's still alive and still healthy. You can get idle currents down to just a few microamps, and you're right in the same power budget as Sigfox or everybody else. Obviously, when you're transmitting for LTE Cat M1 today, that can be up to 23 dBm, which is quite a bit of power actually for these devices, which does necessitate things like supercaps or a little bit bigger batteries than maybe like a 14 dBm Sigfox device might need. But still very power efficient because the time on air at a megabit per second is so short compared to 300 bits per second, where you might have to transmit for many seconds at a time. And the other innovation for Cat M1 is extended discontinuous reception, or EDRX, which means I need the ability to reach from the server or from the network side down to a device asynchronously and send commands. This might be a streetlight controller. I might need to wake up the device for firmware transfers, etc. And really the innovation here is allowing the node to tell the network how many hyperframes of 10.24 seconds it wants to sleep periodically, which could be up to 40 minutes at a time. So it allows your device to be pageable without transmitting up to 40 minutes in between, which is very, very power efficient because those paging windows are very short and you're not transmitting in those windows. You're just maintaining a sync with the network. And there is a periodic check-in where the device does have to transmit so that the base station knows it's still connected. Some advantages of LTE Cat M1 for the class of devices that we deal with, which are battery-powered sensors, controllers, or other devices, is that you have very good US-based coverage coming very soon. In Q1 of next year, Verizon, AT&T will have LTE Cat M1 coverage nationwide. Everywhere where LTE works, Cat M1 will work as well. This includes in buildings, on DAS systems, in urban areas, rural areas, etc. Obviously, there needs to be 4G coverage for the system to work. It's not going to work out in the middle of nowhere where 4G hasn't been built up. But if you look at the Verizon coverage map, you'll see that there's actually very few places where that's true. Another advantage of the system is that you can connect directly to the TCP/IP network, which really means that your device is, for all intents and purposes, right on the internet, right there at the edge. So you can connect direct from that device to any server you like and vice versa, which is very powerful architecture. And with really fast data rates, relatively speaking, at a megabit per second, you can do so much more than you can do with a simpler, traditional LPWAN device, which might be limited to a kilobit per second or less. And these devices can be very power efficient. When you couple the high data rate with the low idle currents, your power budgets are right there where they are with every other technology that we're talking about today. To compare it quickly to narrowband IoT, which is another standard that I'll talk about next, there actually is better uplink power utilization than narrowband IoT because the on-air data rate is so much faster. You're transacting faster, so your time on air is shortened. When pretty much any of these devices are transmitting, they're not any more power efficient than any other one. They're all using, a Class E chip scale amplifier or something like that, which is drawing a pretty standard amount of, milliwatts per, dBm of power being transmitted. Some considerations, though, if you're considering LTE Cat M1 for your application, is that power budget is really yours to manage. You have to, as the application designer, think about putting the device into PSM, putting it in eDRX, and managing the architecture so that you're not needlessly draining the device. And this is something that we at Link Labs really focus on with our M1 devices, trying to make that even easier for customers. Another thing is that carrier firmware upgrades do get pushed down over the air to the modem without your control at all. And during that transaction, you're burning power as you're receiving packets, running a bootloader, rebooting, and you have no control over that really as a customer. So early on, I would expect that features and things are going to be changing. So there will be some cycles for FOTA, but it's not, I don't think, going to really eat into the power budget significantly. Again, I've said there's areas with limited coverage. There's no denying that, but obviously there is no LPWAN technology that's deployed anywhere close to what 4G is deployed, at least in this country. Excuse me. And then, system costs are going to be slightly higher than other LPWAN technologies. These are sophisticated chipsets. You need SIM cards, a separate microcontroller, level shifters, et cetera, et cetera. And then you have to implement LP or IPsec or IP security on your device. You're on the internet, and if you need to manage the ability of that device to either connect, or to not accept connections from the internet, not get scammed. You might want to use a VPN or some carrier service to help with that. And then you have the IPR risk, or the IP risk, that comes with using 3GPP technology. There's a lot of licensed patents and other things that are a part of implementing 4G, and the companies out there that license those patents will probably want to make money off your successful Cat 1 deployment, which is why buying finished systems or buying modules that have IP protection could be important. Finally, you need to consider certification. What we sell at Link Labs for M1 is already carrier and 3GPP certified, but if you go out and start at the module level, you need to budget for the time and the cost of getting a carrier certified. I think it will be a simpler and cheaper process than has been the case for Cat 1 technology before, but still something to consider. All right, some key takeaways for the M1 technology. It will be available definitely by mid-2017, if not earlier, nationwide in the US. Definitely not going to be deployed in other parts of the world as quickly. There aren't 4G deployments in other parts of the world, which is why the narrowband IoT technology that I'm going to get into might be deployed there first. It provides a very power-efficient data transport at relatively high speeds. And the module costs are probably going to be in the $15 range, and data for hundreds of kilobytes to a megabyte or two will be in the $1 to $3 a month range, which is pretty reasonable for a lot of use cases. And as we'll talk about, there are use cases that still can't afford that, and that's where other technologies make more sense. I think it's definitely important to look for Cat-M modules and chips that are designed specifically for Cat-M and don't require a larger Linux environment to be booted up for 20 seconds when you're coming out of power saving mode, because that'll just burn up your battery. We at Link Labs are partnered with Sequans on their chipset for LTE-M, and really, really happy with power performance we're seeing from that. Just a quick shameless plug about the Link Labs solutions in LTE-M. We are certifying through PTCRB and Verizon a communication board, which is this top board, which has the LTE-M chipset and a host microcontroller with an open source project where our customers can write their application-specific code and run their code against a simple API to push and pull data from their server. This board underneath is an open source design for sensor and power boards where you can have anything from GPS, IO sensors. There's a whole gamut of sensors and power that you can implement underneath, which we think is going to be a really great out-of-the-box experience for customers. Just quickly, we're doing this communication host board in LTE-M. Soon we'll be supporting narrowband IoT. And that, of course, also supports our core product, which I'll get into later, which is Symphony Link. That plugs into this open source power and sensor board, which could be battery powered, solar powered, DC powered, AC powered. And we have a growing array of sensors that can plug into that. And then they fit into standard enclosure, both indoor and outdoor, that could be customized quickly to add things like connectors, buttons, labels, etc. White labeling is a big important piece of what we're doing as well. And then on top of that, we have the option to do subscription and data and device management for LTE-M to implement things like, handling, addressing, payload control signals and firmware to devices that are sleeping a lot. That's complicated. Handling firmware upgrades, and then just managing and pooling large pools of subscription to Verizon and AT&T is a valuable thing, especially for some of our smaller customers. All right, so that's LTE-M. I'm sure, Glenn, there's a few questions trickling in over there. We'll get to at the end.
There's one question we can address right now. It asks about LTE Cat M1 coverage in Europe, and I'm sure people are asking also about NB-IoT.
Yeah, Glenn snuck out a second ago, so he missed me answering that question. But yeah, like I said, there's not as much LTE ubiquitously across Europe. I mean, it's certainly in cities. But because it's relatively free add-on from a technology perspective, I think it'll be supported where 4G is in Europe. But we certainly see operators looking harder at NB-IoT, which I'll get into right now in Europe and Asia, than we do LTE-M. NB-IoT is a whole different type of technology in a way that LTE-M1 is LTE done in a simpler way inside of the LTE construct. Narrowband IoT is a completely different technology that kind of came out of a company called Newell and Huawei, and has been designed to fit inside of a 200 kilohertz GSM or UMTS channel. And it can be deployed as a standalone in 200 kilohertz. It can be put in a GSM channel. It can be put in the guard band of LTE, as you see here, or it could be put inside of you could put a bunch of NB-IoT channels inside of a resource block of LTE. I don't really see that happening as much because that's pretty valuable spectrum for higher speed connections, handsets. Carriers make a lot of money off selling data gigabytes at a time, and that would be a less efficient use of that spectrum for doing LTE. So I think you'll see a lot of refarmed GSM and 2G spectrum go to NB-IoT over time. But it's pretty different. It's much slower data rates. It's 200 kilohertz, 144 kilobits per second on the uplink at the maximum rate, and it goes down from there. And it's also half duplex. There's a perception in the market that these chipsets are going to be a lot cheaper than M1. I don't really think that's true, because if you look at all of the pieces of the puzzle that need to go into these modules and chips, there's just a slightly different baseband processor required, which is kind of in the pennies of cost difference. So I think you'll be in the $10 to $15 range, at least for the first few years. Some advantages of NB-IoT, again, the hardware prices are pretty good. The link margins are really good. The data rates are much better than other LPWAN technologies that we're going to get into next. And it does support advanced use cases, where you need acknowledgements and transfer files and this kind of stuff. And there's potentially less IPR risk. This is a new technology that came up from kind of a different tutelage, so to speak, than LTE. So you may have fewer patent holders, holding out their hand for licenses, but that kind of remains to be seen. And it does have much better bidirectional data than most unlicensed band LPWAN technologies that are out there. Some considerations, for our US audience, there have been no announcements about NB-IoT. I'm sure that it will be deployed at some point, but the real operator focus in the US is M1. There's obviously a monthly subscription. There's not probably going to be a TCP IP direct connection from the node. There is going to be some sort of proxy server, which is more like a LoRaWAN or a Sigfox model. So you'll have to interface kind of up the stack from where you would if you were using M1. And I've already talked about availability. And there's also no mobility built into the standard, meaning that if you go from one cell to another, you have to do an idle rejoin request, which is additional traffic. So devices that are mobile or moving around will pay a power penalty compared to M1, where neighbor cells and handoffs and stuff are handled as part of the LTE standard. All right, some key takeaways. The way I like to think about LTE-M versus narrowband IoT is that LTE-M is like LTE Lite. It's LTE stripped down, whereas narrowband IoT is traditional LPWAN on steroids. They've brought up the unlicensed band type technologies to a really sophisticated level. But I do think there is kind of there's a class difference between M1 and narrowband IoT. Narrowband IoT is a great technology for sending sensor type messages, but not really data streams. You're really kind of limited to a message type architecture. Deployments are probably at least a year away, and in the US it may lag significantly behind that. I've already talked about module cost. It may be less than 15 service costs. We don't know. I haven't discussed pricing with any operators in narrowband IoT. It's a very, very new space. And I just want to go out on a limb here and say that I think that the general market perception of the advantages that NB-IoT has over LTE Cat M1 don't really hold in terms of the power consumption, which I think is actually better for M1 due to the faster data rate. The cost, because I think the chips are so similar, and most chip manufacturers are probably going to do the exact same chip fabric for both. And coverage, which there's zero deployment of NB-IoT today, whereas there's a lot of deployment of 4G, and you just need to upgrade, Ericsson or Nokia software to implement it. So I'm not as bullish about the big advantages of NB-IoT. Though, if you have unused 200 kilohertz spectrum in your portfolio in your mobile operator, this is a good technology to put there, and that's probably going to be what drives it into the market, rather than the technology advantages it has over LTE M1. All right, now we're going to go kind of back to the more traditional LPWAN players and talk about those for a little bit. Sigfox is really the company that we can all thank for creating the market here. Just to get a little technical for a second. What Sigfox does is they transmit very narrow, what is essentially differential binary phase shift keying or amplitude modulated minimum shift keying in very narrow channels at a very low baud rate across hundreds of uplink channels in a couple kilohertz of spectrum. And it's completely asynchronous, meaning the devices just wake up and they often transmit 3 times on 3 different channels and hope that their message was heard. There's very limited downlink with Sigfox because any time that base station is transmitting, it's not listening. I think they have implemented some limited downlink to do like a couple acknowledged messages or a couple bit control signals a day, but Sigfox, their core model is 12 bits a few times a day, or 12 bytes, excuse me, a few times a day. Very simple devices, very power efficient, very low cost. That's their niche. And they use stock UHF RF chips from everybody from Scilabs to Microchip. Pretty much I've seen most of the UHF chip vendors support a Sigfox stack. And it's actually a little bit of an art to support BPSK on a commodity UHF chip, which is pretty cool tech if you're into that. But we like Sigfox a lot. It's an interesting technology. Some advantages for Sigfox: great hardware prices. You can buy the chips you need to implement for a lot less than other technologies. It's hard to jam, which is one of the reasons that they've been successful with some customers in the security space in Europe. Is you can walk into a house or a bank or a building with a jammer, and you're not jamming the alarm that's got Sigfox because it's talking to a tower a mile away, and your jammer's nowhere close to it. Whereas a synchronous or 3GPP type technology that requires on a back and forth to establish a data channel would be jammed in that use case. I've already talked about how it's simple to implement. On the consideration side, very small data payloads. So it's really a technology for meter reading and other sensors that don't have a lot to say. And don't need to stream data or do anything super complicated. Or if they are, they need to do a lot of processing to kind of get the story down to a few bytes before it's transmitted. At least in the U.S. In the Americas, the coverage hasn't fulfilled the promise or the hype around deploying in hundreds of cities on a certain timeline. We still see very little coverage in Sigfox in the U.S. And I think honestly that goes back to it goes back to the unlicensed spectrum. If you're coming from Europe in the 868 band and you think that the 900 megahertz band is analogous, man, you got some learning to do, because the 900 megahertz band in the US is like a war zone compared to this nice green pasture of 868 in Europe. And that's because we've got a lot of different licensed users in 900 megahertz with no duty cycle limit. So you can transmit all day long as long as you're frequency hopping and don't violate the time on air or are spreading your energy sufficiently. But nobody can transmit if they're a frequency hopper on the 900 megahertz band for more than 400 milliseconds. Sigfox in Europe and 868 transmits for, I don't know, like 2 or 3 seconds at a very low data rate. When they come to the US, they squeeze that down to 400 millisecond and jack up the transmit power to try to compensate for the link. But when you couple that with an elevated noise floor, they're probably 10 to 20 dB worse link than they're able to achieve in Europe. And then finally, a lot of people we talk to, point out the vendor risk. This is a company that's really sticking their neck out in terms of, capitalization and growth strategy to provide a lot of coverage. And, for sophisticated OEMs that are trying to architect and spend a lot of money on a solution that's going to take them, 5 or 10 years in the future, there's some risk there. So if there's a network for Sigfox where you want to operate and you have a simple, infrequently transmitting sensor, it's a good choice. Modules are cheap or chips are cheap, and the data cost can be less than $1 a month. All right, now we're going to talk about LoRaWAN. So LoRa, if you're not familiar, is a physical layer technology which is created or really owned by Symtec, who makes and licenses the chips in the space. We'll get into LoRa a little bit on the next slide, but it's a very simple but chip scale technology that has very good sensitivity and kind of really baked in various data rates and baseband processors and stuff, which makes building a system like LoRaWAN really easy. The LoRaWAN technology utilizes what I call the dumb gateway smart cloud, where all the gateways in the network are all listening on the same channels, and all the packets are going up to the cloud where they get decrypted and processed. And one of the cool things about LoRaWAN is they have a hybrid business model where you have both carriers that are looking at deploying LoRaWAN networks, but you can also, as a business or an individual, buy gateways and technologies, from a provider and implement a deploy it yourself technology. And that is, I think, one of the keys to their success up to this point. And this little diagram over here just kind of shows, this is a Class A LoRaWAN message going up in one of these 8 channels, and then you have a fixed time offset until if this message requests an acknowledgement when that gateway responds to it. And I have this gray bar here to show that while the gateway is transmitting, it can't listen. So any devices that are trying to talk during that period, the gateway can't hear it. And it also clips any messages that are really close in time that don't maybe only overlap a little bit as well. Which is one of the reasons that we see for customers that have more than just a few devices or are trying to send more data, we see a lot of collisions with LoRaWAN, which causes a lot of packet error rate. There's a couple papers and sources down here that have modeled that out, but you can see even for a network that only has a few hundred messages a minute, your packet error rate can be over 20 or 30%. Which is fine for applications where maybe you're reading a meter often and losing 20 or 30% of the message isn't a problem. But we often at Link Lab see applications where getting the data through is critically important. This diagram over here from a different paper shows that as your channel load approaches full capacity, your collision rate is over 80%, which isn't surprising. This is an Aloha technology. Aloha networks are known to have about 18% capacity. But when you couple that with this unmanaged uplink downlink problem, you have a lot of collisions that are happening that are unmanaged, and it results in message loss. So some considerations for LoRaWAN: great hardware prices. There's a great ecosystem of gateway and module vendors out there. It's pretty simple to implement, and it's one of the only do-it-yourself options available in the LPWAN space. And there's a good ecosystem of vendors. Some considerations are the way that LoRaWAN was designed is to have a cloud server or a Mac server receiving the streams from multiple gateways where they get processed. So you have to have this cloud server in the loop and connected to the devices with a low latency connection. There are some vendors that have tried to take that network server and put it on the gateway, but that's not really how LoRaWAN was designed, and that actually necessitates you having to manage the keys from individual devices onto individual gateways and manage the pairing that way. Again, I talked about message loss. Above about 15% capacity, you're losing a lot of messages, and if you add acknowledgments to the equation, you're losing even more. LoRa, because of the way they've implemented their baseband process, has a limited dynamic range of in the 20 to 30 dB neighborhood, which means if you have a node that's close to the gateway and a node that's far away, the node that's close, if it's co-channel with the node that's far away, will prevent you from hearing the node far away. So just something to keep in mind with the system. It also has fairly complicated key management, which is necessitated by the fact that this technology is deployed by mobile operators and that need to know identity, and authentication and security for billing and other reasons. So if you're implementing in a do-it-yourself scheme, you need to plan for a unique set of keys per device that then gets transcribed over to the server in order for you to have the connection work. For the EU, LoRaWAN is designed to operate in a band that has a 1% duty cycle, and that applies to the gateway as well as to end nodes. So that can limit the amount of data that the system's able to transact. You also have the issue of shared channel interference. So you have, if an operator is operating LoRaWAN in unlicensed spectrum and you're trying to use it for your application in the same spectrum, you're sharing the same channels and you see their traffic, they see your traffic. And back to my previous slide, it doesn't matter if it's your traffic or not, it's still hurting your packet error rate because your LoRa modem is decoding that packet whether it was yours or not. And there's also some additional complexities that I'm not going to get into that are a little bit in the weeds that require you really at the application layer to handle things like varying MTU sizes and also implementing acknowledgements and retries all the way up the stack kind of at your level to make sure that your devices and your application is working correctly. So some LoRaWAN key takeaways: it's a great do-it-yourself option if you have a simple application with maybe only a few dozen sensors who you can manage and deploy yourself. Identity and provisioning can be a little complex, so if you're trying to scale to thousands or tens of thousands or hundreds of thousands of devices, the bookkeeping of the keys and key pairs and the server can get complicated. Message delivery is not guaranteed unless you're using acknowledgements, and if you're using acknowledgements, then your capacity is severely limited, so you kind of got to balance all those things. And you may need multiple gateways in your system to ensure that whilst one gateway is acknowledging, another one's listening. That's really the way the system's designed to operate. And finally, firmware upgrades over the air aren't really possible. There's certainly people that have implemented ways to, multicast or stream traffic down, but because the system's completely asynchronous, anytime the gateway is transmitting down to nodes is time that it's not listening, and it might be losing more traffic that's trying to come up. Just to take a step back about LoRa, LoRa is a really great layer 1 or physical layer technology. We're huge fans of it at Link Labs. And just like LoRaWAN is a stack built on top of LoRa, the Link Lab Symphony Link system is a very different stack, also built with LoRa at layer 1. We've created what we call Symphony Link as a system that addresses the more stringent use cases of industrial enterprise IoT customers that need 100% message acknowledgements, firmware upgrades, et cetera. So we spent a lot of time and energy with our pretty sophisticated engineering team to redesign a LoRa-based system that can take advantage of the really great link budgets of LoRa, but need to add in additional sophistication at the protocol layer. So this is a synchronous and slotted system where we have a variable boundary between uplink and downlink. There's a one-to-one pairing between a node and a gateway, or a node and a repeater, with different provisions to join and scan for other networks, interference mitigation. There's a whole lot of features. The intent of this webinar is not really to get into Symphony Link as much. Certainly can answer any questions about it, or we have resources. Just wanted to position that and the role that it plays in the market. Some of the advantage of it is a flexible architecture. Because the MAC process is completed on the gateway, it can be deployed without the internet as a standalone system. You can have edge processing on the gateway where you're mirroring traffic up to the cloud. That's how we implement lock control systems and other security devices. Firmware over the air is probably the #1 industrial requirement that Symphony Link is used for, so that you can upgrade firmware on devices after they're deployed. We have customers that are pushing new firmware weekly to devices that they've pushed out into the field. Repeater devices are lower cost access point, or not access points, but devices that proxy traffic in between the end node and the repeater that have the same range as the gateway. And for applications like demand response or smart city applications where you're trying to cover a huge area, it's a very powerful architecture. You can have one gateway connected to a bunch of solar-powered repeaters that are covering a huge area, all in a coherent system where all the key management encryption is all being handled. We have some really innovative ways of doing 100% acknowledgements of all traffic on the air, both uplink and downlink, which is really critical, along with a quality of service scheme that allows you to suppress unimportant traffic at the expense of, or while letting important traffic get up to the gateway. And then we have a fixed large MTU, so the application can just send us up to 256 bytes at a time. We'll handle all the sub-packetization. We have true dynamic data rate, so we're adjusting our transmit power to address that dynamic range issue I mentioned, but also selecting the right spreading factor so that as the link is constantly changing, we can address that. We also are partnered with licensed spectrum partner MDM Spectrums, who allows us to sell and operate Symphony Link in licensed spectrum for really critical applications in utilities, oil and gas, telematics, safety critical applications where you need that dedicated spectrum to operate really important asset monitoring or control. Some considerations, obviously it's a limited vendor selection, something we're working on and partnering around. Again, it's a limited data rate as well. We're a little bit faster over the air than LoRaWAN at about 1 kilobit per second, but that's still pretty limiting in terms of customers that are trying to stream a lot of data. And finally, our European variant is still in beta release. It's a very complicated system in terms of the regulatory environment. It has no duty cycle limit. It's implemented the frequency agility and the listen before talk schemes, We do have customers developing systems with it, and we hope to have that fully compliant early next year. Some other technologies that I'd love to get into, and I know somewhat about, that I just don't have time to get into. Ingenue is a company that uses a 2.4 gigahertz spectrum, which is globally available, which is nice to do spread spectrum networking. They're big in the market. There's a lot of interest in that technology. They're like a Sigfox deploying networks in cities. They're building out, like Tampa and Dallas and other places to do, I think, kind of outdoor type use cases. Wi-Fi AH is a 900 megahertz Wi-Fi specification with lower data rates that's been specified. I haven't seen any AH access points or technologies on the market yet, but certainly something to watch in terms of like a do-it-yourself medium range wireless technology that'll be direct to IP. Waviat is the small company from Russia that does ultra narrowband systems, a lot like Sigfox, but even slower data rates for utilities and other applications. And the waitlist community has a couple different specifications and standards around doing LPWAN technologies as well. Definitely something to look at. Just a word on standards. Standardization is really important in wireless to ensure interoperability. But in the early days, innovation can be really slowed down by the standardization process. And I think it's important to standardize technologies at the right time, and also provide ways to have IP protection, which allows private R&D investments and innovation on the standards. That's the model that 3GPP and IEEE have adopted, which has been really powerful, which allows for free, reasonable, and non-discriminatory licensing of IP that gets contributed to standards to make them better, and be able to address a larger market. Any questions so far, Glenn? Or are we going to wait till the end?
Let's wait till the end.
All right. So how do you pick? How are we doing on time? Gosh, it's taking a lot longer than I thought. So how do you pick? One of the first questions you should ask yourself is, where do you need the technology? If you only need connectivity where you deploy it, obviously a deploy it yourself technology would be a great fit. LoRaWAN, SymphonyLink being chief among those. If you only need it in some cities and you know where those are, and there's a network operator that's deployed there, like a Senate LoRaWAN network or Sigfox or Ingenue, that can be an option. But I think if you need indoor coverage in cities, you need to either do it yourself or use 3GPP. I haven't seen any LPWAN, call it non-traditional networks, like Sigfox or others, deploying networks with enough density to provide 40 dB of signal margin at the window, so to speak, so that they can go into the building, into the back room, like you can with your handset. Those networks they cost billions of dollars to deploy, which is why SymphonyLink technology often gets deployed specifically in a building or a plant to provide that level of margin, and we use repeaters and other things to make sure that everything can connect and work well together. Next, do you need bidirectional data? Do you need to have 100% message acknowledgments and firmware upgrade, do control signals, do multicast? Here, I think you're down to SymphonyLink. I know Ingenue supports most of those features, and the 3GPP technologies I mentioned do as well. Note that SymphonyLink, our technology, is the only do-it-yourself or deploy-it-yourself option in these class of use cases. And how many end nodes do you have per area? If it's a sparse network, you only have 2 devices, you may not be able to capitalize in your business model the cost of even a LoRaWAN gateway, where $1 or $2 a month, to connect an LTE modem to maybe 2 sensors that are deployed in a refrigerator somewhere might make a lot of sense. But if it's dense and you've got hundreds of devices or dozens of devices that are sending megabytes a day, that's where do-it-yourself technologies make more sense. If you have really mobile applications, you need devices to be able to roam and you don't really want to control them, you almost have to use a network. But just be aware, like I said, some don't really have handover and might spend more battery and have more latency as they're moving around a lot. And if you're not sure, you don't know how you're going to sell or where your device can operate, it almost requires you to use a ubiquitous 3GPP type network. And then what's your timeline to deploy? If you need to get to market now, you need to use one of these low power technologies tomorrow, then a do-it-yourself option like SymphonyLink or LoRaWAN is your only option. If you can wait 6 months, obviously the deploy-it-yourself options are still a great one, but that's when M1 is going to be in the market. We'll be supporting that as well. If you have a year or 2 to wait, NB-IoT will also be in the market in many markets, so keep an eye on there. And then if you're kind of 2 years out, still thinking through product ideas, all of the above will still be there, but there'll be new technologies. 5G is working on machine-to-machine type technologies, and then there's probably a new technology that we haven't even heard of yet that'll be out by then. That's the fun part of being in wireless. And then just a note here, UHF spectrum, ISM bands, every country's got different regulations. One of the beauties of using 2.4 gigahertz in Wi-Fi, or even Anjanu's case, is that it's a global standard. Sub-gigahertz is not the case. The Americas, Australia, the FCC countries have adopted one standard, and Europe, Africa, Middle East adopted an ETSI standard, the 868. But countries like China, Japan, South Korea, have slightly different variations, and some countries don't even have an ISM band sub-gigahertz, so you can't use a deploy-yourself technology there. Just something to keep in mind if you've got global ambitions for your product. Just a real quick thought on some different use cases out there that we see really driving us forward. The first is defined area asset tracking. This is doing monitoring, tracking, you name it, in places like hospitals, logistics centers, factories, etc. Often, combined with GPS or other technologies. I'm going to make Glenn give me some more water. One of the really successful products we've seen in this space is called AirFinder, which is an iBeacon-based Bluetooth proximity tracking system where you have Bluetooth proximity back to reader devices that are then backhauled via Symphony Link, and then the location information can come out via an API or an application. Check it out. It's a pretty cool use of this type of technology, and really a hybrid type use case. Probably our biggest market at Link Labs is industrial equipment control and monitoring. And the primary driver here is third-party devices that are being sold into or deployed into factories or other places where the OEM does not have a data network. The factory owner might have a great Wi-Fi network, but they're never going to let the manufacturer of a pump put data on that network because of IT security concerns. So to get things like fault code, calibration values, usage metrics, et cetera, out of these facilities, technologies like ours and others that can cover a huge area with a really lightweight infrastructure and often are backhauled via cellular, create a great opportunity to provide this kind of standalone data network. And finally, commercial consumables is a big market for us, where businesses that sell things like CO2, gas, lube oil, anything that's being consumed in a commercial setting where knowing the consumption rate can drive efficiencies through the delivery and supply chain is a very powerful use case, and one that we're working on with several customers. My final thought before we get into questions is that unless you're a network operator, and even if you are, connectivity is just a piece of the solution. It doesn't, quote unquote, really matter what technology you use, as long as it works for your use case. It has the features that you need to go to market, whether you need firmware upgrades or not. And building the rest of the application, the business model that makes sense using the technologies that are available is probably the most important piece. And we work with a lot of customers. Link Labs' real value is our service enablement of being able to take customers from an idea all the way through deploying and building an application in as much of or as little of the stack as we need to play in. So with that, I'm going to, I've got some backup slides. I'm going to post these slides online separately. You can look at those. And we'll now turn to some questions. So Glenn, what's...
So unfortunately, we only have about 10 minutes for questions because we have a hard stop at 2 here. And if you want to ask questions after the webinar, feel free to go to forum.linklabs.com. There's a dash between link and labs. One question that came up in several different ways is the availability of LTE, Cat-M1, NB-IoT, Sigfox, Injinu, LoRaWAN, etc. in X location. So,
right, yeah. Right. Yeah, I mean, it's certainly the responsibility of those different providers to make those things known. I know Sigfox has got a deployment map. You can zoom in anywhere in the world and see their RF propagation. LTE M1 is not deployed anywhere, and it won't be deployed in the U.S. until the end of Q1 next year. But it will be deployed around the end of Q1 next year. I'm certain of that. Injinu, has deployed some light networks in some cities in the U.S. LoRaWAN networks, I know Senate is probably one of the big providers in the U.S. They have, hundreds of base stations, mostly for propane tank and fuel oil monitoring. And then you've seen some providers in Europe, Orange and others, make announcements about LoRaWAN. I'm not, 100% sure exactly what the coverage is, but
yeah, the easy way to find out is ask to put a device on a network, and if you can do it, then it's there, and if you can't, then it's not.
Right. Prove it to me.
Next question. Every IoT device will need firmware updates and security patches after the device is in the field. LPWAN vendors talk about thousands of devices on a gateway, but how do you handle being able to push firmware to all of those devices in an LPWAN network?
Yeah, that's a great question, and that's probably one of the biggest drivers of why SymphonyLink has been so successful. That with a Sigfox or a LoRaWAN technology, you're really not able to update the firmware. So it really is a one-time chance to get the firmware right. The way that we manage being able to stream firmware is that we, tell a device to go into a firmware mode, and we allocate a certain amount of every frame to transfer the firmware, bytes at a time until those images are complete. We're only talking 10 to 50 kilobytes of flash data for these devices. We're not, talking about megabytes here. If you're talking megabytes, you probably need to be on LTE M1 in order to get that amount of firmware over the air. But it's a really complicated problem. I don't know how many man years at Link Labs has been spent in implementing firmware over the air on LoRa, but it's pretty significant and definitely a multi-million-dollar investment on our side.
Since deployment efforts can sometimes be significant cost drivers to the actual deployment of the networks and devices, which LPWA technologies can be set up to automatically connect to a network without user intervention, and what are the security implications of this architecture?
Yeah, so it depends on if the key pair is known. So like a LoRaWAN technology, if you put a key pair into a device and then put it in your network server, it can join your network without any additional steps. One way that we've made SymphonyLink a auto provisioning system is through a PKI service, so that the node requests to join, and then the server goes and looks up its public key in a database to create the Diffie-Hellman session. That's a really nice model because it allows us to ensure that the gateway is a real gateway and the end node is a real end node. PKI security is considered kind of the gold standard there. But yeah, essentially some sort of way to have a pre-shared key or a shared secret to create a secure tunnel is required. So that's why managing more and more of the end-to-end stack is important. And it's definitely a challenge for operator networks. Even if it's LoRaWAN or if it's a SIM card from Verizon, there's more complexity there because they want to keep the wrong people off the network, and when the right people are on there, they want to know who to send the bill to.
What exactly is an IoT platform? And with so many options out there, how do you select the best IoT network, server, platform, etc. for your use case?
Yeah, that's a tough question. What is an IoT platform is a tough question to answer. I would say at the most general level, an IoT platform is some software, some software package that has bundled up a bunch of the, I'll call it foundational requirements of ingesting data, storing it in a database, processing streams, and running rule sets, and hosting UIs. There's a lot of providers out there that have made those pieces a lot easier, so you're not, kind of starting in your Java environment on day one trying to create a whole end-to-end application. But what we found is that every application out there does require some level of customization, and you do have to write a lot of custom code if you want to create a really sophisticated IoT platform. Specifically around LoRaWAN network servers, there are plenty of providers in that space that connect to LoRaWAN gateways and process the MAC data and put it up. But I think it's really comes down to what's the cost, how easy is it to integrate with. I can't really give you a good answer there.
Can you comment on the localization features of the various LPWA technologies?
Yeah, most of these technologies, whether it's Sigfox or LoRa, aren't really suitable for doing native localization, and it's a function of the bandwidth. The ability to measure the time of flight of an RF waveform is really a function of its spectral bandwidth. And at either 10 hertz, 100 hertz for a narrowband technology, or 125 kilohertz for LoRa, your ability to resolve path length differences for multipath is limited. And so your accuracy, especially in urban environments, might be around a kilometer, which is fine for use cases where is it in the city, is it not? But in terms of like the dot on the map, you need to use another technology like Wi-Fi scanning, where you take the Wi-Fi data and you put it against like a Google or a True Position database to locate yourself, or using GPS. The AirFinder application I mentioned earlier uses Bluetooth proximity as that way of like knowing within 10 meters where a device is. But yeah, in terms of native localization, it's a tough problem. The 3GPP technologies at a megahertz of bandwidth with LTE, you're starting to get a little bit more accuracy, but I think even those would still require an additional localization technology to be very accurate.
We have time for a couple more. Anything that was product specific, whether it was for LoRa, Sigfox, SymphonyLink, LTE-M, we'll answer offline because this wasn't really designed to be a product pitch. But here are a couple of questions that are a little broader. You talk about the limits of Aloha network causing a lot of collisions. What are some strategies such as listen before talk that you might be able to use to avoid those collisions?
Yeah, I would say the best, listen before talk as a way of mitigating collisions obviously only works if the two devices can hear each other, which for a lot of these large star networks isn't usually the case. I'm in this house, you're over in that house. I've got to put enough energy in the band for you to detect me. So it's this hidden node problem. The best way to mitigate the Aloha problem is through slotting and through management, where you basically either align a mask in time and nodes kind of pick, which is how SymphonyLink works, to align nodes to certain slots. That kind of organization drives about a 2x improvement in capacity. And then from there, uplink and downlink timing, but all of these things require synchronicity, which isn't built into either the Sigfox or the LoRaWAN standard. So they I think just because of that architecture will always suffer from a little bit of capacity issues related to Aloha structure.
And the last question we'll have for the day, and again, any other questions that come up, please feel free to go to forum.linklabs.com. Is there an upper limit on the number of devices that can communicate on any of these networks?
I always answer that question that no, there's no device number limit, except the only limit is the channel throughput. So if you have 1 million devices attached to a gateway and they all transmit once a year, you're going to be fine. If you have 1 million devices trying to transmit every minute, you're in big trouble. So it's really a function of how often they're talking. The only caveat being that for a highly managed system like LTE-M or narrowband IoT, there is a limit to the number of sessions that the base station can kind of manage, and that's probably in the hundreds of thousands at most. But I'm sure that Nokia and Ericsson will continue to improve the ability of base stations to handle more and more connections as these balloon in the next 10 or 15 years. But beyond that, it's a function of modeling. We've got a lot of models and simulators that allow us to say if a SymphonyLink network is overloaded or what the capacity is. And similar studies have been done for LoRaWAN as well. All right. Well, with that, thanks again, everybody, for tuning in. We're going to send out a copy of this recording to everybody that registered, so look for that, and I'll also share the slides out. And please log on to the forum site. I'm sure I'm going to spend the rest of the day and night answering questions on there, which I actually really enjoy. So look for me on there and shoot me any questions. Thanks again. We love the space, and we love being part of some really fun IoT solutions, and we'll talk again soon. Thanks.